today's class I will just show you some demonstrations through the laboratory videos. I will take you to our XRD lab and then show the equipment details, how the X-ray diffraction equipment look like and what are the primary components and how one would perform an X-ray diffraction experiments in a polycrystalline material. So, you will get a basic idea from this, though you will not be able to do other detailed experiments since it is only a part of this material characterization course. I thought it would be a very nice idea if you have some detail about how the equipment will look like and what are the basic details about in XRD missions. So, if you look at the screen where I started showing, this is the Bruker X-ray diffractometer, and you can see that it is all enclosed in a big box. You can see it in a long shot, and you can also see our one of the scholars in our department is going to operate this machine for us, and I will just show you the details one by one. So, this is X-ray diffractometer and you have the power console here and on and off and everything. So, it is a long shot, and what you are going to look at again from now we have opened this equipment. Now, you are seeing the details of the diffractometer. What you are seeing in the background, backside, the big circular disc is a goniometer. It is called a goniometer, and it is also referred as a diffractometer circle. And then what you are now seeing is everything in a close-up shot, and do not worry, you will be seeing this for a very long time. So, you get the details. So, this is the specimen stage where your specimens are kept, whether it is a bulk sample or a powder sample. A bulk sample is directly kept on this, whereas the powder sample is mixed with some medium and it is kept on a glass slide or something like that, and this is a specimen stage. We will talk about it much more detail. So, what we need to know from this equipment is the basic components. Some of the basic components which you require is the X-ray source. This is the X-ray source, and from where we will talk about some slits and through which the X-ray beam comes out, and then it is made fall on this specimen here. So, and this is a detector. This is a detector again which has got lot of slits inside. We will discuss about the role of slits, and then you have an X-ray detector in this case. So, the primary component is X-ray source, a sample stage and a detector. You can see that all these three are shown in this, and one important thing you have to understand is the X-ray source and a detector is kept intentionally on the goniometer circle. You just see that the X-ray source and the detector are going to be on the goniometer circle, or you can say the diffractometer circle. You just observe these details for some clarity. These are all an XY movement for the specimen stage. We will discuss about the importance of this movement. Okay. The specimen also can go in that semicircle fashion in this manner. So, what I would like to do is, before our scholar perform the experiments, let me also explain some of the basic components. Like you can see that what I would like to explain here is, I will just stop this video here. This is the goniometer circle, your X-ray source as well as the detector are kept in the diffractometer circle or goniometer circle, and the specimen is always kept in the center here, the center stage. We will now just discuss the basic requirement of keeping the sample in the center of this goniometer circle, and there is we will talk about X-ray optics before we do that experiment. So, what I will do is, let me draw a line diagram on the blackboard in order to appreciate what you are now seeing. So, I will draw a focusing geometry. So, what I have drawn is a focusing geometry for X-ray optics. Suppose if you have the source here, and then it goes to the sample and get reflected here, and this is another X-ray source which is falling on the sample in the point B and get focused here in F. And you see that the angle between this is 2 theta, and this is alpha, and this is alpha, and you can have the relation here with the circle inscribing the angle. And what you have to keep in mind, whenever you have the X-ray source which goes into the sample and get back to the point F, that is this is incident ray and this is diffracted ray, are getting focused again at a point F. So, you can say that this is a source of X-ray and this is your detector and this is your sample, for example. So, if this geometry is maintained for all the scanning, for all the scanning, for variable 2 theta, this is completely maintained. For all the, wherever you keep variable 2 theta, this geometry is maintained. And we can write so this is also called a Bragg-Brentano diffractometer, where this kind of geometry is used. And then I will draw one more schematic which will show the parafocusing of the goniometer as well as what the sample you are going to scan during various angles of 2 theta. So, I will draw two more figure, then I will get into the discussion. So, what I have drawn here is two types of 2 theta angle, how this Bragg-Brentano geometry, or I would say Bragg-Brentano par focusing method, which is being adopted in this particular diffractometer. So, you have this is a diffractometer circle or goniometer circle, which I showed you in the video, and this is your sample, which I said that. So, these two, we are talking about two circles here. One is diffractometer circle or goniometer circle, the other is a focusing circle. So, what is this focusing circle? Depending upon the 2 theta, it is going to vary. So, you see that you see your as I said that your specimen detector and the source should be in a circle. So, assume that this is a focusing circle and this is your diffractometer circle. Depending upon the 2 theta, it is going to vary this way or this way. So, in this case, you see that this is the specimen and the specimen normal, and this is the incoming source, and this is a diffracted beam which is focused, and then you see that the specimen is kept in the circle on the perimeter of the circle of focusing. So, depending upon the 2 theta, you can see that the 2 theta is becoming smaller, then you see that the focusing circle is also becoming smaller. As the 2 theta becomes bigger, then you see that it is your focusing circle also. So, this geometry is preserved, and that geometry is called Bragg-Brentano geometry, and this kind of focusing is called parafocusing, and which is being adopted in this particular diffractometer. So, with this background, now you go back and look at the video, you will be able to appreciate what I am trying to say. Now, if you look at the video again, what I will do is, now you can see the goniometer circle, and then let me finish that before I go. Goniometer circle, and this is the source, and this is a detector, and this is a sample which is kept in the center of the goniometer circle in order to maintain this focusing circle, which will be here. Depending upon it is going to vary. Right now it is small because now the 2 theta is here, this 2 theta is, this is a sample, you draw a straight line, and this is the diffracted beam. So, this angle is 2 theta. So, that is going to vary, then you see that the focusing circle is also varying. So, now we will look at much more detail about this. This is about the basic components of the diffractometer. We will now show some of the important components here. Okay, this is what we are now seeing here in the screen is the X-ray tube. What is a typical X-ray tube one would look at? Okay, so now you have the better view. This is an X-ray tube where you have the target material which is inside, and later we will also open this and then show you some of the details of the X-ray tube, that this is how the X-ray tube will look like, at least you have some idea, and which will go into that source what we have just shown. So, of course, this the whole tube is under the cooling system, and then you have the beryllium windows through which your X-ray comes out. Beryllium windows are transparent to X-rays. So, that detail I would like to finish. So, have a close look at this X-ray tube. So, now we will move on to an experiment now. Before even go to the experiment, let me stop here and then explain little more details about this. So, I said that the X-ray source is here and it is going to come out through this exit window, and you remember the X-rays which are coming out of this window is completely divergent beam, and it is divergent beam in all directions. So, it need to be controlled. One of the way to control this divergence is by through slits, and we have a typical slits which are popular, and then which are kept inside this, and then it is being made to fall, or collimated beam is made fall onto this specimen. And similarly, the detector also will have a lot of slits and filters. Please remember, we are interested in taking only a particular X-ray beam, for example K alpha, and you will in general, if without the slits, you will also come across K beta and so on. So, the other radiations are blocked by these filters. For example, K beta is suppressed, you cannot eliminate completely, but it can be substantially suppressed as compared to K alpha radiation. The filters are here, and this is a detector. It could be a semiconductor device as well. So, now I think that is the basic idea you should have about this X-ray diffractometer, and then now we can even look at how experiment is being performed in this machine. And please remember, this stage is a rotating stage. It can rotate 360 degrees, and also it can move on a semicircle in the stage which I have mentioned. Now you can see that a typical stage movement. In order to save time, I am just cutting some of the shots so that you will be able to see this. You can see that the source and detector are moving, but still that focusing circle is maintained here. So, in order to mention that preserve that Bragg-Brentano geometry, parafocusing geometry. You can see that the stage is moving. Yeah, now it is measuring the beam with various angles, 2 theta angles. Now we will see that the stage will also move in the semicircle fashion in order to one of the primary requirement or the use of this the stage movement is you will be exposing the sample in all possible diffracting planes. For example, if you are interested in particular plane, or if it is a powder sample, the statistically important data you will be able to generate if you are able to rotate this stage in all the 3 directions like this. See that the sample is coming towards the front and X and Y movement, and you will be able to appreciate that. Now we will see that the sample will move in this direction, it will rotate in this direction, that also you can see. Yeah, what you are now seeing is a top view. The sample is now completely rotated. You can see in that semicircle stage, it has moved. Now it is coming back, you can see that. And these rotations are completely exploited in the case of texture measurements, which we are not showing. We are trying to just show the instrumentation detail and what are the possible tilt angles and so on. And we will simply look at the basic diffraction data which comes out of this sample. The sample which is being used is I think alpha silicon oxide powder, and you will see that kind of diffraction data which will be obtained from this experiment. You can see that specimen rotation completely, it is a 360-degree. Okay, this is just for your information, the X-ray tube which we showed earlier, now it has opened up. This is your anode material. It could be, you can change this target material based upon the specimen you are analyzing. It could be a chromium or chromium target, copper target and so on, depending upon the type of sample you analyze. And what the other dismantled part is, okay, this is a close-up view of this anode, just for your information. And this is that beryllium window which we talk about, through which the X-rays will come out. This is a dismantled part. Not just an important here, but just for an information how the X-ray tube parts are shown. So we will now quickly do a one full set of complete experiment and then generate an X-ray diffraction pattern, and then we will see what we get. So the data collected from the instrument is completely analyzed by the interface software, and we will show you what kind of data you get, and then how it is, how the background everything is filtered by the software, and then you can have a look at it. So let the fresh experiment starts with all the possible 2 theta angles. We will not hold this video for the complete experiment. We will quickly go to that final result. So you see that the sample is kept here, and then it is being measured at various 2 theta angles. I will skip that step because you have now you know that how this diffractometer functions. I will quickly forward this video in order to save some time. Okay. Now you are seeing that how you are dynamically getting that signal. We are viewing through the software. You see that typical X-ray diffraction peaks are coming on the screen. So all these 2 theta corresponding peak belong to a characteristic peaks of alpha silicon oxide, which I just said, powder. A polycrystalline diffraction pattern, typical polycrystalline diffraction pattern will appear like this. And you can compare this 2 theta value and go to a JCPDS database to identify particular crystal system. Of course, you have a large number of software parameters to derive the data from, I mean information from this basic data, and this is a typical X-ray diffraction spectrum you will get. So, with that what I think is you have some basic idea, if not very detailed idea, how the X-ray diffractometer look like, and then how the source and the specimens are kept, and how the detectors are kept, and what is the basic data you get out of this equipment. And I hope these equipments and these small demonstrations gave you some basic insight about an X-ray diffraction laboratory. If you are not able to access this laboratory, at least you know now how these equipment look like and how, what are the basic operations behind this. We have not done an elaborate experiment here due to the constraint of the time, but I hope you had some basic idea, and now you can connect what we do, I mean theoretically what we study in the books, and then what practically you can do it in the laboratory. When you have an opportunity to look at these equipments in some other labs, now you will have some idea how it is done and how the basic data is generated. So, that was my intention of doing this laboratory demonstration. Thank you.